Good morning, everyone. Can you hear me?
Yes, sir.
Yes, sir.
You can hear some background noise also. Sorry for that. Uh, okay, so last we started with duality theory. As I said, it's a very interesting theory. So now we have divided the problem in primal and dual. And simplex method, which we have learned so far, is known as primal simplex. Because maybe today or next class we'll look at dual simplex method, and that takes care of all the irregularities like greater than equal to negative right hand side. Everything can be taken care of by dual simplex method. Now coming to I was talking about that primal simplex method works with primal feasibility and try to find dual feasibility. I will try to explain you with this example that it works. It's primal simplex algorithm works with primal feasibility and wants to achieve a dual feasibility. The moment it achieves the dual feasibility, actually you have your optimal solution. So let's try to understand. Let's look at iteration 0. So as I have already told you, the values of dual variables can be found below the coefficients of what do you call coefficients of slack variables in the zeroth row. So we will focus on this part. Okay, so let's look at the first one. If you look at the primal side, primal problem, which is this one, maximize g equals to 3x1 plus 5x2, and dual is minimize w equals to this much. Now, if you look at the value of x1 and x2 at this iteration for primal problem, what is x1 and x2 equals to? What is the value of x1 and x2 at this iteration?
0, 0.
0, 0.
0, 0, very good. 0 and 0. And what is the value of dual? 0, 0 and 0. So y1 is 0, y2 is 0, y3 equals to 0. Is this correct?
Yes, sir.
Now check whether which one amongst primal and dual, check whether primal is feasible or not. By plugging in into the constraint x1, x2 equals to 0, check whether primal is feasible or not.
Sir, it's feasible.
Now check dual with the dual variables. Is it feasible?
No, sir.
So that's why if you put 0, 0, 0 here, not objective function, sorry. If you put here 0, 0 greater than equal to 3, it is not feasible. So what we can learn here is primal, feasible, dual, infeasible. Now, if you plug in the value of x1, x2, 0, y1, y2, y3 equals to 0 in their respective problem, what do you get the value of g equals to?
0.
What do you get the value of w equals to?
0.
Now let's look at the second iteration. What is the value of x1 and x2 in this iteration? X1 is still 0, x2 has a value now equals to 6. Similarly, if I look at y1, y1 equals to 0, y2 equals to 5 by 2, and y3 equals to 0. Again, check which one is feasible and which one is not feasible. Of course, you already know primal simplex always look for the feasibility. This has to be feasible. Just a second there. So you can check, you can plug it the value of x1 equals to 0 and x2 equals to 6, and you can see that the primal problem is feasible. Is that correct? It has to be, because we are working with the primal simplex whenever we ensure that this part is always greater than or equal to 0, right? Now plug in the value of y1, y2 and y3 and see whether it is feasible or not.
It is infeasible.
Infeasible.
It cannot be feasible. You plug in y1, y3 here, check. y2 equals to 5 by 2, right? Five is greater than or equal to 5. That is fine. That is being satisfied. What about y1 and y3? Is 0 plus 0 is greater than or equal to 3?
No, sir.
So again, primal feasible, dual infeasible. As far as g equals to w, you plug in these values, you will get 30. Even if you put 5 by 2 here, 0, 0 these guys, it will give you 30. Now the last iteration where we know that primal is optimal now. x1 equals to 2, x2 equals to 6. y1 you have got equals to 0, y2 3 by 2 and y3 equals to 1. Plug in these values and tell me which one is feasible.
Both are feasible, sir.
Both are feasible. So primal is feasible and dual is also feasible, and this is the condition for optimality. Now you plug in the value of g equals to w, both will come out to be equal to 36. Okay, so only at the optimality, keep this in mind, only at the optimality dual solution becomes feasible. In the homework assignment later, not now, I will give you an example where you will be able to draw it graphically and see that how each of the primal point corresponds to a dual point. And every primal feasible point corresponds to a dual infeasible point, and every dual feasible point corresponds to a primal infeasible points. And the point where both primal and dual are feasible to their respective problem, that is your optimal solution. Only at the optimality dual solution become feasible. The moment dual solution becomes feasible, you are at the optimality. So don't you guys find it very interesting? As I said, it is one of the most interesting for me in linear programming, that while solving primal simplex, actually you are solving two problems, primal as well as dual. Okay, so the reason they are associated with the slack variable, if you look at this problem, to make it an equality, I have to add slacks, right? Each of the slack is associated with the corresponding dual variable. We'll soon see theorem called complementary slackness theorem. If slack is 0, dual variable will be positive. If slack is positive, dual variable will be 0. Just to give you an idea, when any of the software tries to solve it, many a times the problem is so big that it cannot solve completely. So what it tries to solve both the problems simultaneously and tries to find there's something called duality gap. So maybe problem is such a large that you cannot really reach to the optimal solution. So it will leave you to one of the corner point which is feasible, and it will give you a duality gap. What that duality gap, I will try to explain. Just give me a second, I need some water. Okay, so suppose I'm just trying to explain in a two-dimensional thing. The primal problem is standard form, maximize G equals to Cx, and dual problem is corresponding standard form, minimize W equals to YB. Suppose this is where feasibility happens. So this is the feasible optimal G star, and you already seen that that will be equals to optimal W star. Now, at this point, let's say iteration 0, we start with G equals to 0, right? When you try to solve the dual problem directly, because this is maximization, so I will start from an inferior solution and try to reach to a optimal solution. Especially, likewise in dual, I will start with a again inferior solution, which is I'm trying to minimize, so higher value, and I will try to reach here, which is G star equals to 36. So this region is called suboptimal. This is called superoptimal. Both of. Similarly for this one, this is suboptimal and this is superoptimal. What suboptimal and superoptimal means is, if you are at a solution, let me try to show here. G equals x1 and x2 both are equals to 0. So your G value is 0. Then you move to the next solution. Not coming up to 0,6. G was equals to 30. Again, you are in the suboptimal region. You have not yet reached the best value, which is the optimal. If you go outside this region, what you will get? You will get an infeasible solution, but G value will be large. Does that make sense? Suppose this is my feasible region. If I go beyond this point, I will be having a G value, sorry, not G star, a G value greater than 36. You agree? Outside the feasible region. Does that make sense?
Yes, sir.
Yes, sir.
But that is not feasible. So that's why we say super optimal. I have a better objective function value, but it is not optimal. Similarly, when you try to solve dual, it is a minimization. So it will start with a large value and try to come down to a smaller value. Okay, so the moment, so when you try to maintain the dual, primal feasibility. So primal feasibility in this region, correspondingly, it will be super optimal here. So it will become infeasible. When you go to the other side, here, primal becomes infeasible and dual becomes feasible. So there is only one boundary point where primal and dual both will be your feasible and hence optimal. Now suppose when I'm trying to solve a very large problem, it is taking a lot of time. So we generally talk about duality gap. So suppose from dual side I have reached until this point, from primal side I have reached until this point, and this difference is your duality gap. So generally we give duality gap in the range of duality gap should be less than 1% or 2%, something like this when you are trying to solve it. Because as I said, some problems are like 100,000 variables, 10 to 20,000 constraints. It takes hours and hours. Sometimes when I told you I was working as a consultant with JDA, one of the problem for Amtrak, it's American railway system. It was taking 5 days to solve a network optimization problem. So we cannot really work with the optimal. So what we used to take a feasible solution which is close to the optimal. So suppose my problem is trying to solve this problem. So there are a lot of points. So rather than taking this, I'm okay with whatever I get until here and I proceed with that solution. Does that make sense, guys? Any questions? See, keep in mind when I'm saying that I'm solving from this side, when I solve from this side, it is primal simplex. When I solve from this side, it is dual simplex. So keep that in mind when we are trying to solve. Now I will tell you theorems on primal dual relationship. They are very important. As I said, they are of lot of interest when we are trying to solve a large scale problem. Theorems on primal dual relationship. So first one is theorem 1 is called weak duality theorem. So what it says, if X is feasible solution for primal, and Y is a feasible solution for dual, then, and again I'm talking in terms of a standard form. Standard form means primal is maximized G equals to Cx, Ax is less than equal to B, and dual is minimized W equals to YB, YA is less than equal to C. Then Cx is less than equal to YB. What exactly this theorem is trying to tell me? Can you tell me, any one of you? Because there is no point calling your names because you do not respond. Yes, guys. What does this theorem trying to tell you?
Sir, I think as y is always means y is come from more value to less value, so it is always more than when it is in feasible solution, and x is
No, this is the side where it is feasible, primal,
yes.
and this is the side where dual is feasible. So suppose there is a point X. There will be a point Y here. So corresponding Cx will always be less than YB. Does that make sense? This is where the values are increasing for G values or W, whatever you call G equals to W. So this is the direction in which it increases. So dual, since it is a minimization problem, it starts with a higher value of W value and comes to a lower, which is minimum. I mean, just to explain, when you try to solve a maximization problem, we draw lines like this. So we start with this inferior solution and try to reach to a best solution. Is that correct? This is maximum.
Yes,
When you try to minimize, suppose I'm trying to minimize, suppose my feasible region, okay, so since I'm trying to minimize, okay, so I may start from a solution from here, but minimum happens here. So my objective function line will come like this. First this. Does that make sense? So this theorem actually gives you an upper bound on primal solution. Does that make sense? Is this clear, guys? Feel free to discuss if you have any doubt. Yes, someone is trying to say something. The second theorem is called optimality criterion theorem, or it is also known as strong duality theorem. What this one states, If X star is optimal solution for primal and Y star is optimal solution for dual, then what will happen? If X star is optimal solution for primal and Y star is an optimal solution for dual, what happens?
Cx star equal to by star.
Y star B. So this is where optimality theorem, which we have already seen. And the last theorem, which is of most importance, it's called theorem 3. It has actually no, theorem 4 is last theorem. This is main duality theorem. Main fourth theorem is very important. It's called complementary slackness, which I was talking about earlier. Well, this one state is if both primal and dual problems are feasible, then they have optimal solution such that their optimal value of objective functions are equal, which we have already seen. G star and W star both equals to 36 in the example which we are working with. And finally, theorem 4. This is most interesting one. It is called complementary slackness. Complementary slackness theorem. Now onward we will refer it as CST. It says let X0 be the feasible solution for primal and Y0 be the feasible solution to the dual the X0 and Y0 are optimal to their respective problems if and only if Y0A minus C into X0 plus Y0 into B minus AX0 is equals to 0. Read this one carefully. As I said, it is very important. So I want you to understand step by step. So let X0 be the feasible solution for primal and Y0 be the feasible solution to the dual. Then X0 and Y0 are optimal to their respective problem if and only if. What does this represents? Y0A minus C. Let me write it here for your easy reference. Maximize G equals to Cx. Ax is less than equal to B. This is primal. Dual is minimize W equals to YB. YA is greater than equal to C. So what does YA minus C represents? If I want to make it a equation, can I add a surplus variable, let's say V naught for time being? That will make it an equation.
Yes.
So this is nothing but a surplus variable. So YA minus C equals to V, that is surplus. So this is dual surplus. This is primal variable. This is dual variable, and this is primal slack. To make it more understandable, let me break it down into two equations. So let's say U equals to U1 to UM are the slack variables primal in primal problem, and V equals to V1. Okay, if V are the surplus variable, how many V's will be there for an n variable m constraint problem? How many? So
N.
how many?
Sir, N.
And very good. So good. You guys are following. So there will be n variables. Now using U and V, we can represent V. Let me use another color. Vj0 into xj0 equals to 0 for j equals to 1 to n. Sorry, n. And yi0 and ui0 equals to 0 for all I equals to 1 to m. Now look at this equation, and that will tell you why the names complementary. Why the name complementary? Okay. What is Vj?
Dual surplus.
Dual surplus.
Dual surplus. What is Xj?
Primal variable.
Primal variable. If I'm saying two variables are getting multiplied and equals to 0, what does that, what it tells you?
One of them is 0.
One of them is 0 and other is, because all the variables, the way we design our LP problems, all of them are greater than equal to 0 for standard form, either surplus, slack, normal variables. So if one of them is 0, other will be greater than equal to 0. So when I say that the surplus in the dual problem is 0, then I can say the corresponding primal variable will be greater than equal to 0. So all in all, this theorem, what it is, I will also show you its another use. Suppose I gave you x0 equals to 3,2 and y0 equals to 5,6. I just gave you and I said that it is feasible. How do you check whether it is optimal or not? If I just gave you primal is given to you, you have converted its dual. I gave you, okay, listen, 2,6 is feasible to the primal and 5,3 is feasible to the dual. Now you want to know whether they are optimal or not. If these points satisfies this equation, so I have broken this into two parts. You can see this part and this part, because all of them are greater than equal to 0. So I have broken them into two parts. If I'm able to show that this is being satisfied, I can say they are optimal solution. If it is not being satisfied, they are just an feasible solution, but not optimal. Clear? Now, let me show you. So this is the word complementary has come. Complementarity comes from if one of the surplus or slack is positive, corresponding variable will be less than equal to 0, greater than equal to 0. So another example of use of this theorem is very interesting example. Suppose I gave you maximize g equals to x1 plus 2x2 plus 3x3 plus 4x4 x1 such that x1 plus 2x2 plus 2x3 plus 3x4 is less than equal to 20 and 2x1 plus x2 plus 3x3 plus 2x4 is also less than equal to x1 to x4 greater than equal to 0. Okay, now you want to solve this problem. How can you solve it? Simplex, right?
Yes, sir.
How many variables you need to deal with?
4.
6, yeah.
Yeah, yes.
Forget the slack variables. 6. Now convert its dual. Tell me its dual. One by one. So minimize W. What is the objective function? Say I give y1 to this constraint and y2 to this constraint. So what is my objective function? Yes. What is the objective function? Minimize W equals to for dual.
20y1 plus
20y1
as
plus
compared
20y1 plus 20y.
Good. Now let's write one by one the constraints. Tell me the first constraint.
Sir, y1 plus 2y2
y1 plus 2y2 is
greater than 0.
the coefficient here is 1 into x1, not 0 into x1. Right? So
Yes, sir.
similarly, you can write 2y1 plus y2 is greater than equal to 2. 2y1 plus 3y3 is greater than equal to 3. And 3y1 plus 2 y2. y2 is greater than equal to 4. y1 to y4 greater than equal to 0. Just check if I have written everything right or not. So if 4 variable primal problem is converted into how many variables dual problem?
Sir, 2 variables problem.
2 variable problems. You can solve it using graphical method. I'm not going into that detail. I'm directly given you y1 equals to 1.2 and y2 equals to 0.2 and w equals to 28. So this is the solution I have for dual problem. You can draw it graphically and find it. Now with this solution, we will try to find the values of x1, x2, x3 and x4. So first we need to convert it into equations. So x1 plus 2x2 plus 2x3 plus 3x4 plus slack variable we will use u and v's. Okay, so u1 equals to 20, 2x1 plus x2 3x3 plus 2x4 plus u2 equals to 20. This is the primal side. Let's subtract surplus variable from the dual side. So y1 plus 2y2 minus v1 equals to 1 because it is greater than or equal to constraint. So we need to subtract the surplus. 2y1 plus y2 minus v2 equals to 2. 2y1 plus 3y2 minus v3 equals to 3. 3y1 plus 2y2 minus v4 equals to 4. Is this correct? Any mistakes? Just look at it quickly. So I have added slacks u1, u2 on the primal side and subtracted surplus v1 to v4 from the dual side. Fair enough?
Yes, sir.
Yes, sir.
Now let's write our complementarity conditions. So CST conditions. Okay, so tell me what are the CST conditions? U1 0, that is the primal slack into dual variable should be equals to 0. Similarly, U2 0 into Y2 0 equals to 0. Then all X and V combinations should be equals to 0. So X1 0 into V1 0 equals to 0. X2 0 into V2 0 equals to 0. X3 0, V3 0 equals to 0. And X4 0, V4 0 equals to 0. We already know Y1 1.2 I have find, Y2 0.2, W equals to 28. So without even solving this problem, can you tell me the value of G, optimal value of the objective function for primal?
28, sir.
So this is equals to 28. Let's try to find the value of X1, X2, X3, X4. So let's start with the first condition. Y1 0 equals to 1.2. So what is U1 0 equals to?
0.
0. Similarly, Y2 0 is 0.8. What is U2 0 equals to?
0.
What does it tell you about the primal feasible region? Both the slacks are 0. So these two equations are active or inactive constraints. Both the slack variables equals to 0. So what does it tell you about these two constraints?
Active.
Both of them are active. The solution happens at the intersection of these two constraints. Now let's start solving for x1s. So since you know the value of y1 and y2, can you tell me the v1, v2, v3 and v4 values? What is v1 equals to?
Sir, 0.6.
What is v2 equals to? You need to just plug in these values and tell me v2, v3, v4 values.
0.6, sir.
0.8.
V1 is 0.6. What is v2 equals to?
0.8.
Is it coming 0.8? 2y1.
No, sir, 0.6.
2.4.
Yes, sir.
Huh? 0.6 again. What is about V3 and V4?
Zero.
What is V4?
3.6. 0.
0 again. Okay. Nothing biggie. Just you have to put y1, y2 value in this equation. You will find v1, v2, v3. Now let's start. Now in the third equation in CST, v1 0 is 0.6. What can I say about x1 0?
0.
Similarly, v2 0 is 0.6. So I say x2 0 is also equals to 0. Good enough?
Yes, sir.
Let's come to v3 0 equals to 0. So x3 0 should be greater than or equal to 0. Or not even equal to, because it cannot be 0. It has to be greater than 0. And v4 0 is again equals to 0. So x4 0 is greater than 0. So these two numbers should be greater than 0 equal. How do I find x3 and x4? Any ideas?
Sir,
But-
we have two equations in 2A.
So we already know these two guys are zeros. So we are left with just these two. So we know x1 0 equals to 0, x2 0 equals to 0, u1 0 equals to 0, u2 0 equals to 0. Plug in these values. So I'm left with 2x3 0 plus 3x4 0 equals to 20 and 3x3 0 plus 2x4 0 equals to 20. Solve this equation and give me x3 0 and x4 0 equals to.
Sir, 4 and 4.
Okay, so based on CST you get y1 0 and y2 0 equals to 1.2 and 0.2. I mean this you have to find, at least one solution need to be known. x1 0, x2, let me put a star, now they are optimal solution. 0, 0, 4, 4, w equals to 28 and g equals to also 28. Interesting.
Sir, what is the significance of this y1 that the sign 0 above it?
Which one?
Like in each variable we use 0 na in
0, I'm saying that I know a solution which is a feasible solution. I want to check whether it is a optimal or not. The moment it satisfies all these conditions, I will change it to y1 star and y2 star.
okay.
Okay. So is it interesting, guys?
Yes, sir.
Yes.
Mathematically, if you see it feels very interesting. So let's also try to understand some, inferences from what we have done. So let's start from here. If primal variable is positive, like in case of x3 and x4, the corresponding dual constraint will be satisfied at the optimality or not? Are you understanding the question? If a primal variable is positive, like in this case x3 and x4 is positive, then what happens to the corresponding dual constraints? They will be satisfied at the optimality or not. That means v3 and v4 will be 0. Make sense?
Yes, sir.
Yes,
So,
sir.
corresponding, if primal variable is greater than 0 or positive, then corresponding dual constraints are active constraints. The solution lies on those constraints. Similarly, if a primal constraint is strict inequality at optimality, that means which one actually इसमें तो UN है नहीं, but what I'm trying to say, if a primal constraint is a strict inequality का मतलब क्या हुआ? UIs are greater than 0 or less than 0 or equal to 0. Are you guys following the question? If the primal constraint, इस केस में वो नहीं हो पाया है, but if a primal constraint is a strict inequality at the optimality, that means UI is greater than 0, then only it can be strict inequality, otherwise it will be equality. Make sense?
Yes, sir. Yes, sir.
Or in other term, if slack variables in the primal problem is greater than 0, what happens to the corresponding dual variable?
It has to be equal to 0.
It will be equals to 0. The dual variable will become equals to 0. So these are the important insights from the duality theorem. Now suppose if I give you just look at these theorems, how they are used. ठीक है. Suppose for this problem, I will give you the problem which we already know. Let's look at the window glass problem again. Maximize g equals to 3x1 plus 5x2 and x1 is less than equal to 2, 2x2 is less than equal to how much? 12. 3x1 plus 2x2 is less than equal to 18. And I gave you x1 0. Okay, I gave you this problem and ask you find an upper bound on this solution. How can you find that? So what you need to do is convert its dual. So 4y1, so x1 is less than equal to 12y2 plus 18y3. y1 plus 3y3 is greater than equal to 3 and 2y2 plus 2y3 is greater than equal to 18. Just put any number which satisfies these constraints. Give me any number which satisfies these two constraints. Any number of your choice.
Five comma 5.
Huh?
5 comma 5.
5,10.
5,10. Okay. If you give me 5,10, what would be the corresponding W value equals to? $140. I'm talking about y1, y2, y3. Give me any number which satisfies this. So you have given me 5, 10, 0. So y1 equals to 5, y2 equals to 10, and y3 equals to 0. If you plug in here, what is the value of W?
$140.
140. I can always say G is always less than equal to 140. Is this correct? You already know G equals to 36 in this case at least. So you can put an upper bound on the any solution that is known to this problem. Okay. Now for you to understand how these things work, there is also a very interesting relation between primal dual which I want to tell you. Again, assuming the standard form, based on the primal or dual, we can tell you if primal problem is optimal, corresponding dual problem will also be optimal. If primal problem is unbounded, dual problem will be infeasible. If primal is infeasible, two cases can happen depending on standard form. It can be unbounded or infeasible. Now for you also, I will give this problem to you in your class homework assignment. Try this. I'm giving you a problem, maximize homework practice. For you to understand how things work, it will be very useful. Maximize G equals to 2x1 plus x2. x1 plus x2 is less than equal to 4. x1 minus x2 is less than equal to 2. x1 comma x2 is greater than equal to 0. So what you need to do is first write its dual. Second, solve, not solve, draw. So if this is a two variable problem, what is the dual problem? Is it two variable or three variable problem? Look at the structure of primal. Is it two variable or three variable problem?
Sir, two variable.
So you can draw the graph. Draw graphs for each problem. Okay. Look at the corresponding feasible and infeasible point. Third thing you need to do is solve both problem using simplex algorithm. So definitely the dual problem will be minimization greater than equal to. So you already know how to deal with such problems. So solve both the problems graphically and look at the primal feasible points and dual infeasible points, which is just below the slack variables coefficient in the zeroth row, and see how the transitionings are happening. This is for your own benefit to understand primal and dual. Okay, see how those points are moving and how the infeasible points and feasible points finally. So what you will see when you solve the simplex for both of them in two papers and draw the graph in two different sheets and keep both the papers side by side and see how primal feasible solution and dual feasible solution, how they are interacting with each other. Okay, so you will see very interesting relationship, and again it is beyond the class time, so you have to try it. Tomorrow, not tomorrow, I will not take any extra class tomorrow. On Friday, we will see dual simplex algorithm. That takes care of all the ill-behaved problem. Nothing to worry about converting into big M2 phase anything. You can just proceed with this one that I will teach you on the Friday. Okay, I believe your solution and everything has been, grades have been posted.
Yes, sir.
Any questions? Anything you have not followed or anything? Is the first problem clear? I have tried to write the answer in a very simple words. How you can convert, not always you can convert, but some problems which is non-linear, you can convert into a linear form. Was that solution helpful? देखा ही नहीं होगा तुम लोग, ठीक है चलो. Check that on the exam night. Okay, most probably I will schedule your class test for 25th, the Friday, and tomorrow, no, not tomorrow, day after tomorrow, I will complete the dual simplex algorithm and I will start sensitivity analysis. And as I said, your class test 1 syllabus is until converting into the dual. So until here is your class test 1 syllabus. Okay, if you have any questions, we can discuss. Otherwise, thank you very much, guys. I will see you on Friday.
So what is the difference between unbounded and infeasible? Like,
what is that?
What is the difference between the unbounded region or infeasible?
ये तो यार तुम बहुत गलत क्वेश्चन पूछ रहे हो. You try it. What is unbounded and what is infeasible? Tell me. Jay, don't feel shy. I'm just, sometimes I just say things like you are asking galat question and everything, but I just want to, for the benefit of everyone, tell me what is your understanding of infeasible and unbounded?
Like in infeasible, I think it is means out of the.
Okay, for infeasible problem, what can you say about G value?
For infeasible, G value.
It cannot be determined.
Yes, sir.
There is no feasible solution space. Yes. But for unbounded, whether there is a feasible solution space or not. What is the G value for unbounded problem? G value for unbounded problem is infinity.
Okay, yes, sir, yes, sir, yes, sir.
So there is a feasible region, but it is not bounded. As you keep increasing, it will keep increasing. although it is meaningless, but it is not an infeasible problem. If you add a proper constraint, it will give you a bounded region and you can have a solution. Does that make sense?
Yes, sir.
Good. Any other questions, guys? Okay, I will try to, we have 2 hours on Friday. Last half an hour, I will keep it for class test 1 review. So I will go through some topics. You guys can also come up if you have any questions. I will try to answer those. Okay.
So can you please upload the previous lectures PDF?
Which one I have not uploaded?
So like matrix one.
Oh, okay. I will do it today. Thank you for reminding me. Okay, because of my travel, I forgot, but I will do it today. Thank you so much. Bye bye, guys. Take care.
Thank you, sir.
Thank you, sir.